Hey everyone, welcome to this video in the hand calculation series. In this video, we're going to be describing how to calculate the dose to points that are actually outside of our field. And why might we want to do this? Why might we need to do this? Well, I think it's most obvious that we may need to calculate the dose outside of a field. If there's some sort of critical structure at the field edge. For example, if we're doing a 2D whole brain treatment and we're treating the brain, the eye might be collimated out, but right on the edge of the field, and we might want to know the dose that the eye is receiving. So it's kind of a situation like this where our target is covered by the field, and then there's some critical structure right outside the field that we want to know the dose to that critical structure. So how do we actually perform one of these calculations? Well, the concept is kind of abstract, but let's walk through it. Suppose we have a field size of A times B, and that our point that we want to calculate the dose to is a distance C from the field edge. So it's a situation where we have here, so we have our field size of A times B. P here is the central axis, and the point of interest is Q, which is this distance C from the field edge. So next we are going to create some virtual fields. So we're going to surround point Q with a field of size 2C times A, and then add another field of size AB on the other side of that field. And this is kind of hard to understand, so I drew out the geometry for you. So you see point Q is now centered on a field of size 2C times A, and then we add another field of size A times B to the other side of it. So we have point Q is centered on this big combined field and also centered on this 2C by A field. So I'm just copying back the geometry here. So you see we have our big field and our small field. And then to compute the dose at point Q, we just compute the dose from the big field and subtract off the dose from the small field and divide it by 2, since we only truly have half of this situation. And so we calculate the dose with the field size of A times 2B plus 2C, which is that big field. And we subtract off the dose with field size of A times 2C, which is that small field, and we just simply divide by 2. So it's kind of an abstract concept, but we'll work through an example in a little bit, and it's important to note that it's just an approximation, but it is a reasonable estimate of the dose that is delivered outside. Another quick note about this technique is that it ignores off-axis ratios, so it doesn't account for the off-axis difference in beam quality that you see across the field, and the point of interest is assumed to be along the central axis of these two fields here. So now let's do an example problem, and I would like you to first, pause the video and read through the problem statement, which is shown here. So first I'm going to go ahead and draw out our geometry. So here's the geometry we're dealing with. We have a 10 by 10 field. We're asked to calculate the dose to a point 5 centimeters from the field edge. And drawing out our virtual fields, we get something that looks like this. And the field size for the big field is just going to be 10 by 30, which you can use that equation that I laid out on the previous slides, or you can just do simple addition here. Probably easier to do the second one. So that's 10 by 30. If you work out equivalent square for that, it's 15 centimeters squared. And then the small field is, of course, just 10 by 10. And our calculation depth in this case is D max, so we are at the calibration condition because we're given the calibration condition in the problem statement. So these are about as simple of calculations as you can get. For the big field, it's just our reference dose times the monitor units times the PDD for a 15 by 15 field size at a depth of D max, which of course is just 1 because the PDD is normalized to D max. Then we also have our total scatter factor for a field size of 15. So our dose calculation equation reduces to the second line. And then for the small field, it's even simpler because the total scatter factor is also 1 because that's how our beam data was defined, and that's the reference field size. So it's just simply the reference dose times the monitor unit setting. So now we can go to our beam data and get the factors we need. Well, I guess in this case, it's just one factor. We just need the total scatter factor for our 15 by 15 equivalent square size, which is 1.033. And then we can go ahead and compute the dose from the big field and the small field. So for the big field, we get 516.5 centigrade. For the small field, we get 500 centigrade because it's the reference condition. And then to calculate the dose to our point, It's just the dose from the big field, subtract off the dose from the small field, divide by 2. So we get a dose of 8.25 centigrade to this point outside the field. So this was a pretty straightforward example, but the same formalism can be applied to any treatment geometry in order to get the dose to a point outside the field. So thanks for watching.